We'll be talking about scikit-learn. Of course, we'll be going through a notebook first today, and Mesh will walk through that with us, and then we'll dive into scikit-learn pipelines. And I found a really good book on SageMaker and AWS. So SageMaker also has pipeline tools, so I would encourage everyone to look into that. And I'll share the link to the book. I think this book just came out recently, last month. It's called Data Science on AWS. Actually, let me share this right now. Let me share screen. This is the book. It is by two fellows, Chris Fregley and N.J. Barth. I think at least one of them, NJ, is working at AWS. I don't know about Chris, but this is a fantastic book that I've I guess browsed through. I haven't had enough time to go through it. I did order a copy, but haven't had too much time to go through it yet. But I look into some of the chapters. It was really good. This book covers about, I think one of the comments said this book covers about 75 AWS services. So it's quite complete. And of course, all the topics will surround with AWS. For those of you who are, let's say, who are just more into PyTorch and less interested in TensorFlow, I would, look into this more, because obviously this deals with SageMaker pipelines. I would assume they would be compatible with something like PyTorch. So, but yes, so instead of TFX, you're using SageMaker pipelines. And you can see, like, that's how they define different processing steps with the SageMaker library itself. I don't know how much it costs with SageMaker. I guess the training will obviously cost some money, and the endpoint itself will cost some money as well. If you're trying to connect that to an API. And you can configure pipeline parameters, creating pipeline. So, you see a lot of familiar steps, but it's all with the Python SDK with SageMaker. Okay, and of course, this you can deal with this on SageMaker Studio, but obviously, this is all just from a library standpoint and Boto3 API, I guess. So it's a very comprehensive book, and covering all the AWS services. And you can also, seems to be the case, you can also use Kubeflow pipelines with SageMaker. So utilizing both tools together, which is also pretty cool. So I would look into this book if you're, I guess you don't want to stick with TensorFlow or TFX. this is also an option. And perhaps down the road, we can even cover a chapter or a session on SageMaker pipelines. So, any questions on this before we start today? Oh, DPI, this book is Data Science on AWS. And it just came out, I believe, last month. Okay. And today we will be talking about the TFX notebook with feature engineering. So let me just share this on the chat again, and Mash will be going over this in a bit. And also we will be covering this GitHub, so make sure you clone down this GitHub. Let me send this as well. Okay, and just to give you guys an idea, we are covering this, right? Scikit-learn series workshop 1. So we'll be talking about some scikit-learn pipeline. And this is a series of 5 workshops, all covering scikit-learn topics. And the next one is serving model with REST API. And then we want to try to deploy our model on AWS. So this book will certainly come in handy, right? So if you're not familiar with SageMaker or AWS, it does have a chapter that covers deploy models to production. So if you want something to read about it and understand deeper level, and of course, not just click and click on a platform, which you can do, but completely from a programmatic level, how do you deploy a model? Perhaps, look into this chapter. So, okay. And we have the 4th workshop, pipeline orchestration with Airflow. So we want to try to see, hey, if we can just do combine scikit-learn with Airflow. And then eventually, this is more on the DevOps or data ops end, in terms of CI/CD pipeline and testing, but it is a very essential component that's a part of this ML ops and the entire cycle as well. So, we're trying to basically cover a pretty comprehensive topic. And as I mentioned it previously, this GitHub is related to this course on Udemy. And if you have a new account or you've never registered a Udemy account, I think it does give you discounts. It's like $20 or something after discount. I think it's absolutely worthwhile to get this course. And this is what this course looks like. I went through some of it and not all of it, but it's quite good. And this is something that we're going to cover quite extensively from the GitHub, at least, not necessarily on the class itself, but certainly on the GitHub. But this is what the course looks like. Overview of model deployment and research about developing a machine learning model, packaging it, serving it on REST API, CI/CD pipeline, differential tests, deploying it with containers on AWS ECS, and some deep learning stuff as well. So this is a really fantastic course that I wasn't able to find anywhere else. So I would certainly recommend you to look into it beyond the GitHub that we'll cover. So, okay. So that being said, let me hand
Yep.
yeah, everything to Mesh. Yep.
Thanks, Wencheng. We're going to be talking quite a bit about just overall pipeline. So let me share my screen. And as Wencheng shared, the first link that he shared, which is the TFX tutorials, Penguin TFT, that's the one that we're going to use. So what I've got here is that Colab notebook that I have running on, saved to my own Google Drive that you can see on the screen. A couple of things to get this started. I just want to, what we'll do begin today is, we've been talking a lot about pipelines. We just started this session as with Wencheng showing us the AWS SageMaker's pipelines, which seems to be one different way of constructing pipelines, but is scalable and flexible enough to use with anything we potentially would need to do. Plus, it allows us to integrate with other AWS services. But if we focus on just TensorFlow and the base TensorFlow with TensorFlow Extended and how it creates the pipeline, that's what we're going to cover here. And then after this, we'll go even more basic, allow Wencheng to introduce us to and walk us through building the pipelines using scikit-learn. So without further ado, unless anyone has any questions, let's walk through this particular notebook. And as I do this, you all can follow along or run it on your own machine. And the first things first, I did have this running, just want to make sure that it actually ran. And it's still running. Yeah, still has it in memory. So I decided just on a lark, not that you even need it. I'm using a GPU accelerator. And once you install the first set of packages, the instructions are, and there's because of a certain deprecation of some package, Google even says you need to restart the runtime. So once you install these packages, loads it up into Colab's memory, restart the runtime, and then we're ready to go. Call the certain packages, and then set up the pipeline itself. And this is kind of what we've discussed before, even in the last class. To construct a pipeline, set it up with a name, where it'll be stored, its path for the model, where the model will be served from, et cetera, as well as calling some of the logging capability. This will be a little more apparent shortly as we go along. More basic files, but here is the raw data that we want to take. It reads this penguin size .csv, which not this one, I did have it up, but it's just, we'll see it in a bit right down here, and it saves it, rename it in this temp location, renaming it to data.csv. And then we can pull the head on it, and here's the raw data file. It's you can probably do I wonder if we can do length. Nope, guess not. There's only head. Guess not. I'm not familiar with some of those commands, those bash commands. Here's the raw file, and then set up the schema. Now we discussed schema earlier in last class as well, when Wencheng walked us through it on how he set up the basic schema using Visual Studio Code. This one looks like this. Basically, Here's the proto file, saves that, and then it's like to me, it looks a lot like JSON, a JSON file, where it does identify things such as all of those columns that would use, the body mass, column depth, column length, flipper length, island, gender, sex, species, and so on. And it does pick only a certain number of those things, but here, this is basically what we're trying to predict, the species. And the species has three values. This is your dependent variable that we're going to set up in the pipeline to try to predict. Anyone have any questions looking at a file structure like this, schema file structure? Okay. So this is already pre-set up. So if we were building a pipeline, this would be something that we would need to construct, knowing what the data file that we're working with and so on. So a good bit of manual work there, but hopefully you do it once and you have your input data coming in, it should always be the same. We're going to skip through the validation. We've already covered that 2 weeks ago. So let's just go straight into the pre-processing and training. And this is where it will save the code that we put here as penguinutils.py. And that will be this. This is what will be the pre-processing code, where it says here are the feature keys that you will use. And the label is going to be that species, which has 3 different values. And put in certain things like batch size for train and eval. Set up the pipeline, the TensorFlow extended pipeline this way. Wencheng, is there anything that you want to walk through with this specific function, like the pre-processing function and the apply pre-processing function? You're much better at it on the Python functions than I am.
Yeah,
is there anything that stands out unique for you? That's special.
I think this pre-processing FN is something that we covered last time, right? So remember, this is a function name that you cannot change. It has to be named after pre-processing underscore FN. And as you can see from that comment, it says TFX transform will call this function, right? So that if you recall what we had, what we covered last week, basically TFX transform component will call this pre-processing FN function and process the data. So in this case, the tutorial itself did not use some of the functions like I think it was called compute to vocab and having a map or a mapping from string to index. And it says right here, we could instead use tft.compute and apply vocabulary in order to compute the vocabulary dynamically and perform a lookup. But in this example, there are only 3 possible values, so they used hard-coded table for simplicity. So for our case, right, for our example, which is a consumer complaint, we actually use tft.compute and apply vocabulary. But in this tutorial's case, they used tf.lookup key value tensor initializer function for that task, and then they just create a table that uses tf.lookup.static hash table. But again, I would use tft.compute and apply vocabulary, for a more complex data set. And and there are some input functions, Mash, if you scroll down.
Apply preprocessing, get serve.
Yeah, if you scroll down a bit more, there's some input functions that the tutorial defines. Basically, they actually call this input function in the run function, which trainer will call later on. So these input functions kind of generate features and labels for tuning and training. And if you see, so these are a bunch of helper functions, basically, right?
Mm-hmm.
And the run fn, if you scroll to the end, the run fn will take a lot of these functions, right? The build correct Keras model, the underscore input fn, which will compile the train data set and eval data set for us, and the build Keras model will build the model for us. Then but all this feeds into this one run fn function, which the TFX trainer component will call upon when it's run. So, and as you can see, you also have a model signature, which has some metadata defined within the pipeline as well. And you have the model.save. Once it's done, you will save the model within a directory that you define and passing in the signature. So, yeah.
So basically, as we walk through it, running the model is always generally the easiest part. We had picked the epochs and so on, and that's just called here, and it's just run model.fit. And when you save it with a signature and model.save. It's the construction that comes before it that, as Wencheng just walked us through, that will be specific to the use case that we're trying to develop. So the pipelines, the complexity of the pipeline will be entirely dependent on how complex the actual use case is. So in this case, we're only trying to, we're feeding it 4 different features to predict classification with 3 different choices. So they hard coded it. If it got a lot more complex, like the consumer complaints table, where there are NLP checks and all of that, then it becomes a lot harder. And so the pipeline would use more complex functions. So setting up the pipeline is pretty much the hardest part. And then I reran a couple of times. So it saves that as the penguin utils.py. And then once we've done that, now we set up the pipeline definition. This is fairly standard: example gen, statistics gen, the schema importer, example validator, and then calls transform, as we defined above. Does it take that py? It was supposed to take the penguin utils.py file.
Yeah, I think it's just passed in as the module file. So module file is the variable that they pass the penguins utils.py.
Where is it defined to the module file should take penguin utils?
If you just control F, it will it should say that. Yeah, it's underneath write preprocessing and training code. So remember the block of code that we just went through, the input fn, preprocessing fn. Go to that block. Exactly, this one, and go to the top, very top.
Preprocessing.
Yep, go above.
Keep going.
Yep, keep going. Right here, module file. Of course.
Module file was defined as Penguin utils. Sorry.
Yes.
Yeah, that's what I was looking for. So module file was already calling. Sorry, missed that, guys.
No worries.
And so here's the module file. Just saw it. Module file. So when it kicks off with transform.
Yeah, and it will automatically detect the, as the comment says, right, transform input data using the pre-processing FN. So it automatically detect the pre-processing FN in the module underscore file dot variable, which takes in the penguin utils.py file. So.
And then that sets it up. Here's where the trainer is defined and what it needs to do. And then that is then the output of that is then pushed out to the pusher. Pusher defines the components. So it goes in sequence, transform, trainer, pusher, after everything else is done. And that's your pipeline, and turn the pipeline. So we run that. Okay. And then we run the pipeline. And this continues, this keeps running, and we end when it shows the component pusher is finished. Doesn't take too long.
Yeah, after this step, you should have the model because it's already trained, right?
And there it is. So component pusher is finished. We do have the model. And here's, if we look in the model directory here, all this. Model is saved. That's it. You can pick, once the model is saved, you can call, with the attributes of those files, you can call the one with the latest timestamp, version control it, all that fun stuff. And of course, because there is a signature, there is a way you could track the validity of the model if it's, it's the one you expect. You can then call it also to test it, to run an inference. So if you put in your own values for Kalman length, Kalman depth, let's just change this around a little bit. 18.3, 6, and body mass. Let's make it a very heavy penguin. And if we run this, these are 3 scores for the 3 different types. And it does say it is the third type, third element still being the Gen 2 species.
Cool. And Mesh, if you don't mind scrolling up a little bit back to the pusher. So if you see here, now we are just pushing this to a file system, like a serving model directory that we defined. And down the road, you always want to, obviously, you don't push your model to your local file system. So you want to push this actually to a directory on the cloud, and maybe on the AI model platform, maybe on SageMaker, maybe on S3 buckets, where you can actually version your models and store all your models there, and so that people can pull your models and or query your model.
I got a question. So where it says serialize to string, let's see, the third to the last line there, it says examples equals example underscore proto dot serialize to string. This is in the prepare an example and run inference code block. It's the last code block. And so my question, yeah.
Which one is that? Which one is that?
The very last code block in the, which is called the prepare an example and run inference. Yeah, that one. Okay. So now it says the third to the last line has this dot serialized to string method, and I'm wondering why we needed to do that. So we built this example called example underscore proto, and then we had to run this method dot serialized to string on. Why did we have to do that?
Well, example proto is just what the input was. These were the values that I had put in, the 7,400 from body mass, heavy penguin, and so on. So that is then.
Can you just type in examples and see what's out of the examples variables?
Sure. It points to memory location. No.
It made it into a string.
Into a string. That's why you serialize to a string.
Yeah, but why does it need that? Why does it? I'm just not familiar with that form of input. I mean, why doesn't it just take the numbers?
Oh,
Does anyone else know the answer?
example proto serialized to string still keeps it looks just like that's examples. I can venture.
Just keep it in the back of my mind.
So apparently all proto messages can be serialized to a binary string using the dot serialized to string method. That's what it is, but exactly why?
Usually serializations for encoding sent over network. Is this distributed or just one server?
That's an interesting point. But if you're spreading it across multiple servers, would that also mean that those multiple servers would also need the same the code runners, these other things that we ran, the other functions, the pushers and so on? That kind of probably didn't make a lot of sense.
Because for TensorFlow, which is Google stuff, protobuf is probably the protocol underneath for serialization to send between servers.
My understanding of protobuf was that it was a data structure.
So, Mash, if you would allow me to share my screen.
Of course. Or do you want to take over control?
Yeah, let me just do that real quick. So this right here, it creates a feature message using tf.string.example. So then you serialize to string. So then it gets to this. So what it says is where was this one? Create message. Basically, I suspect it's probably a feature message. Let's see what it is. That's the source code, I guess. It's probably something that you can pass around more efficiently, maybe. That's what it is. It's a feature message that you could serialize as well. That's what this example has.
So does this have to do with parallel processing and that kind of stuff? Is that why it's being used?
Yeah, that's between, it's like basically exchange information between processes, different servers, especially.
Would that be specific? So would this method be specific to TensorFlow and TensorFlow's use and reliance on protobufs, BigQuery, and so on and so forth? But if we were to switch over to AWS SageMaker pipelines, would they try to do the same thing entirely differently because AWS would have a different stack, if you will?
Yeah, I suspect that's the case.
So it's all part, I mean, just one type of binary encoding, right? So it's if it's protobuf for TensorFlow, it should be the same on AWS as well.
Hmm.
And how much of this would be unique to TensorFlow? So if we were using PyTorch, or even what we will probably go through in a bit with scikit-learn pipelines, would they handle the serializing the model, the output, and everything entirely differently?
I think it depends on whether, I think out of box, TensorFlow is designed to scale that way. But there's three, I mean, basically three type of encoding: language specific, textual, and then binary. So protobuf is one kind of binary encoding, and of course it's Google stuff.
Yeah.
So, but if we use PyTorch, my understanding is depend on whether you run it alone or run it as part of like Kubeflow. If you run it as part of Kubeflow, then the underneath infrastructure take care of that. That's still using protobuf. So the fact is calling that library, it is probably using binary encoding.
So
I mean,
I found this, in order to write these messages as TF records, we need to convert them into Py strings. For this purpose, we can use serialize to string method. So we can update our function to convert the example message. It's basically when you have tf.string.example, it becomes a message. Then you need to convert that. You need to write these messages as TF records to pass around. Then this function basically just converts them into byte strings. So I think right. Yeah, go ahead.
Yeah, so I think everybody is kind of putting together the pieces of the right answer, because Victor said that this is a way to convert the data into a format that works faster, that can be transferred faster among parallel processors. And you said it's converting them to byte strings. And in the book on page 152, and it's in chapter 8, model deployment with TensorFlow serving, I found a reference to protocol buffers. It says, I'll just read from it. gRPC API uses protocol buffers as the data structures for the API requests. By using binary protocol buffer payloads, the API requests use less bandwidth compared to JSON payloads. Also, depending on the model input data structure, you might experience faster prediction as with REST endpoints. And it says the performance difference is explained by the fact that the submitted JSON data will be converted to a tf.example data structure. And that's what we started with, I think. This conversion can slow down the model server inference, and you might encounter a slower inference performance than in the gRPC API case. So yeah, I guess that's the protocol buffers are there so they can speed things up. in the inference side, I think.
So where was this in this book?
Yeah, it's on page 152,
Which chapter?
chapter 8.
Chapter 8.
And if you don't have the page numbers, it's right above
It must
the
be.
section.
Is that
Oh, do you
this
have
one?
the page numbers? Do you have the page numbers?
No, I was just Googling gRPC.
Yeah, Google protocol buffers, because that I think this is the only
Protocol
time it mentions that. And
buffer.
well, let's see, protocol buffer. No, maybe. Let's see.
It's right before model A/B testing with
That's
TensorFlow.
right. That's right. The section called model A/B testing with TensorFlow.
Keep going to payloads.
Yep, right here.
There. Right there.
And that's the part that I read.
Okay. Protocol buffers been using better. Cool. Cool. I think someone else also mentioned something in the chat. I think Nidhi mentioned to read data efficiently, it can be helpful to serialize your data and store it in a set of files 100 to 200 megabytes each that can each be read linearly. This is especially true if the data is being streamed over a network. This can also be useful for caching any data pre-processing. Reference an online TF block. So I think it's just useful to run reading and caching faster at inference when we use serialized format. Okay, well, we don't have all the answers, but I think this is certainly something that we could dig into further with TensorFlow and TensorFlow protocol buffer and TF example.
I have a question
as well.
for folks who may have completed or who did complete Jeremy Howard's Fast AI, all of his code, all of his entire course. Does Fast AI have a pipeline? Because I just looked up the pipelines being used with NVIDIA, and NVIDIA pipelines make reference to using Fast AI for data pre-processing.
Yeah.
And their framework also makes reference to similar things such as train loaders, servers, and so on. Just curious, the world is going to be filled with all sorts of pipeline frameworks.
Yeah, it is. I certainly have run into several of them already. And yeah, and I think, this is, I guess this comes back to, learning in general, just like, if we jump from one to one and we're just eventually overwhelmed with all the tools and stuff. So probably good to just focus on one or two and learn it really well and stuff. So
Learn the basics, the fundamentals.
yeah, exactly. So in something like Airflow can be just used in multiple places. So if you learn Airflow, then you're good to go on many use cases, not just on ML. So yeah. Cool.
Mm-hmm. That's pretty much it on the Penguins pipeline.
Cool. So thank you, Mash. Appreciate it. All right. So let's jump into this GitHub. Let me just give a quick overview, and I want to give everyone like around maybe 15-20 minutes to play through the GitHub themselves and look at the code, and then we can do a deep dive into what the code is actually about and how you actually can construct a pipeline yourself with scikit-learn. Okay, so let me just go into this very quickly. This is tackling a data set that's on Kaggle, and it's quite famous Kaggle data set as well. Let me open it up. Kaggle, Iowa data. It's probably this one.
So
Amos,
Iowa housing data, yeah, used
yeah,
pretty frequently.
yeah. Iowa Amos housing. Amos housing. I could just go into this. See which one is it referring to. 1 second. Just see. Um, it was a competition.
Found it. Can I just send the link on the chat?
Yeah. Might be this one.
Yeah.
Yes, this is the one. This is the one. Yes. So if for those of you who are not familiar with the data set, let me just quickly walk through this. Train. I didn't log in. Let me see. Okay. So we do have the data fields here. So basically, you know, it's MSL Iowa is I guess a city or a town in Iowa state. And this competition was hosted several years ago and has 10,000, almost 10,000 teams. And it's a regression task and more so in, you know, to predict housing prices. And you have train test .csv available here, and you have probably around, I would say yes, 163 columns, quite a number of features. And you have a bunch of, you know, housing related features and sales prices, obviously target variable. You have zoning, frontage, area, street, alley, utilities, shape, lot config, condition 1, condition 2, overall quality, year built, roof style, basement quality, external condition, basement footage, total basement footage, heating, electric, full bath, full half bath, garage type, garage year built, garage condition, pole quality, year cell type, cell condition, blah, blah, blah. So tons of features. Some of the features are quite sparse, some of them are not. And it's a quite fun data set to go through, you know, when you first pick up data science. And it's a quite fun data set to have some EDA done as well. When I first learned machine learning and so on and so forth. So that is the data set that these two folks used. And these two folks are actually, one of them is a software engineer, and one of them is, I think, data science lead working at a corporation. And this guy's name is Christopher. And this lady's name is Soledad Gali, and they kind of joined a team and developed this course in the GitHub as well to talk about how to build machine learning pipelines and stuff. And mostly it's been covering topics around scikit-learn, but it does have some deep learning at the end, not too much. The way how this GitHub is structured is similar to how we structured our practice GitHub as well. And you see, as a requirements.txt, readme.md, and has a proc file that is for Heroku deployment. And if you don't know Heroku, it's basically a deployment or hosting platform for mostly websites. And let me just open it up here. Heroku.
It's a small world. Someone, an analyst who used to work, a manager who used to report to me, is now the head of HR at Heroku.
Very nice. All right, I need to get into. Why does it say Salesforce? Did Salesforce buy Heroku?
I think so.
Really? Wow. Salesforce buying everything. Salesforce also bought what? Tableau?
Yep.
Right. So, damn. All
because
right.
Microsoft had Power BI and they couldn't. They did try to buy it too.
Yeah. Okay. So this is the website, and typically I use Heroku for website hosting, and because it has a free option, a lot of times you can deploy your website for free on Heroku. And of course, you can have production, which is $25 up per month for free. It's code. It's basically code hosting, which means it will take around 20 seconds to 30 seconds for the backend server to load up, and then a user can access your website after 30 seconds of spinning. And
so unique part about Heroku is it's not just giving flat HTML files, it's for web apps. So if you build a web app with your web page, everything else, that's why you'd want Heroku.
Mm-hmm.
The processing backend. Sorry.
And no worries. And production, obviously, you don't have that latency. And what this GitHub or what these two folks are doing is, hey, you can also develop your machine learning model and deploy on Heroku as well. And of course, you can deploy on AWS. You know, they're just trying to go through different deployment options, right? So that proc file is a configuration file for you to host your application or package on Heroku. That's just what it is. Okay. Makefile is basically you have a bunch of commands that go through make commands, and you have your Docker file right here. Basically compiles a Docker image, and this is something that you can deploy basically your container on AWS ECS, and that so this GitHub offers you an option to do that as well. And I actually recently picked up AWS ECS. It's quite a fascinating tool, a deployment option. ECS. And what's fascinating about this is you have something called ECS Fargate, which you can serverlessly deploy your containers on AWS ECS. So Fargate will be able to manage your containers without you managing the servers. and I've been playing around with this for work and deploying containers, a couple containers already. And so this is quite fascinating tool so that you don't have to manage servers yourself, and also your containers become way more scalable as well. So it will be able to deploy more resources if your containers have a lot of traffic. So that is, why are we talking about that? It's because you can also deploy your ML package within a container and just put it on or deploy it on AWS Fargate with ECS. So they're run together. So Fargate is run under ECS. Fargate is just a serverless service that you can deploy that would manage your resources for you on top of your ECS service. But you don't have to. You can manage it yourself with the EC2 machine. Basically, then you would have to deploy your containers on the server that you manage. Okay, so that is that. Let me go back to, yes. So, and this is basically just compiling the Docker. How many of you are familiar with Docker and Dockerfile and play around with Docker containers? Just type in the chat just so I have a quick idea.
Philip, thank you.
Anyone? Okay, haven't used Docker. Thank you, Heather. Anyone else?
Looks like just one so far.
Okay, so should I assume everyone else is pretty comfortable with Docker, or we should cover Docker, because this is actually a very essential tool to master for anyone, and who deals with deployment. And I think it's absolutely great and essential for data science professionals or data professionals to master this and be able to deploy your own package in a Docker container and just deploy it on any platforms such as AWS. So and it doesn't take, there aren't too many great, I've come across several great tutorials, but surprisingly, a lot of them actually go through a lot of stuff that don't cut into the chase, and it because Docker is a large framework, I guess, / library or software, and it does have a lot of material to cover. But in order to do something like this, it actually doesn't take that much time to learn. So let's see if we have time. So most likely we'll be probably covering some Docker stuff then on June 23rd, then because that's when we deploy our model with AWS. So perhaps we can compile a model together within Docker and using the Docker file and try to see if we can just deploy it on AWS. Okay, so let's see. Okay, so used, yeah, that is. Yeah, a lot of data science professionals actually, I'd probably agree with that. A lot of data science professionals just hand their work to the downstream data ops or software engineers or machine learning engineers. Then perhaps they would handle it. But it is actually, I do have to say, it's such a wonderful tool. I can't say praise enough about this tool.
You want your time, rather than letting anyone take time to do the reading, just walk through setting up the Docker container from the GitHub repo, and just walk everyone through so they can see you do it once.
Yeah, so you mean this Docker file?
Yep.
Okay, so what this means is actually just you're pulling an image from Python 3.6.4 and Docker Hub. And if you look into Python, that just means we're pulling from 3.6.4. Do we have that here? Yeah, so this is probably no longer supported, or it's shoved into archives. But these are the tags that are supported, and tags are just versions of images or versions of this package. And in Python's perspective, we're talking about, hey, the latest tags or latest versions come with 3.10, and we're all the way from 3.6. And Alpine is just version of, I believe they're just different versions of Linux, and also different versions. So slim means it's a slimmer version of OS and different builds of the image. And I used Slim Buster for my work, or Slim for my work. So, which means the image size is smaller, and it was enough for my work. But sometimes you might need more functionalities for what you need to do. So, but Slim, I would suspect for an ML package like this, Slim is probably enough, and it's around 500 megabytes. Okay, Alpine is a lot bigger. It comes with a lot more stuff. And when you pull that image, okay, that just means we're pulling that image from with a Python version of 3.6.4, and run this add user, disable password, create the user that will run the app. So you can also create a user, I guess. I typically don't do that. And you can create a work directory. Then everything runs after this will happen within this work directory. So what it means is that when this gets spun up, you have a Linux system. It's probably a Linux system, and you have a Python running on that Linux. And you're CDing into this opt.ml API directory. And you have this arguments, and you have this environment. So you're setting this as an environment, and you're installing some packages, a typical setup for your package, and you're making the run sh executable, and you're I don't know what this chown is, and you are defining the user. What's that?
It changes permissions.
Changes permission. Okay, and you're exposing. So here's what it is. You're exposing your ML package or API at port 5000. And then eventually you run the command bash run sh. So that in this package, bash run sh is the one that runs the entire flow, okay, entire ML flow. Excuse me. And what Dockerfile does is it builds a Docker image for you, and so that you have that image and you can build a container based on top of this image everywhere else. meaning you can, now you have a, image built up from your Docker file. A Docker file is just a definition of how you want to build up your image. And this is the definition, right? And you can deploy or push your Docker image to Docker Hub. And this is what people did, right? These are all images people pushed to Docker Hub. And so Docker Hub, you can do private repositories, or you could do public repositories, and so on and so forth. Those are two of I was just testing, some repositories or images, or you could do on AWS ECR, which is Elastic Container Registry. And again, this is under ECS, okay? So all these container services are all under ECS. And so on AWS, this is where you can save and store your image that you build up from your Docker file. And so if you have a full pipeline, let's say you have a full pipeline, and automate it, you can just, hey, change something and or develop a new version, or upgrade your current ML code and commit your code and pushed, and then recompile this image and push it to this registry. Okay, so think about GitHub, right? GitHub is where you store your code, but container registry is where you store your image. Okay, that's just what it is. It's the same thing. And you can version this, right? You can version your images with tags, just like what these folks are doing with Python images. You have 3.9, 3.8, 3.7. Okay, they're just corresponding to the Python version itself. Okay, so we have some folks chatting.
Yeah. Hate to interrupt you, Wenchang. I have everything set up on my machine, Docker engine running. Do you want to walk everyone through setting up the Docker image so that it is structured and set up on my machine, and then we can walk through the pipeline construction off of my machine?
Well, because the other thing is, this file probably compiles something on top of the pipeline. So we might, let's do that at a later stage, I feel like. But we can certainly talk about Docker more, or we can compile the image today. That's no problem. But that image does something more than just pipeline. It has something to do with the API and all that stuff. So that's something for the next workshop, actually. So you see what I'm saying?
Go ahead.
Yeah. How do we run this code from the repo? Yes. So this code is run. So let's say if you want to train the pipeline, you just run the train pipeline. Okay. And if you want to run, let me just see. If you want to run the entire pipeline, you just basically run this publish model sh, I believe. That's the bash file that eventually runs everything. Input test. And this is the regression model that's eventually packaged. And yeah, so the run.sh, I guess, is the one, or whatever sh bash file is the one that you guys could run. But you have to set up, a bunch of other stuff as well. Again, this is not the focus of this session, as we're just focusing on the pipeline and the structure of this project or this package. And this helps you input test. This helps you to fetch the data sets from Kaggle. And this publishes the model itself. Let me see if, okay, what was the other question? What's the difference between VM and Docker then? So VM has to have its own operating system, and Docker, and there's an image I can Google, VM versus Docker. So yes, can I get a clearer image? One second. So let me share. Okay, I have a great image showing the difference between VM and Docker. So this is the difference between a Docker container and a VM. VM basically has everything, right? So your OS, and you have your application and your libraries. So every VM would have an OS, but a Docker container would just have application and libs and deps, and your OS is down here. Okay.
Libraries and dependencies.
What's that?
Libraries and dependencies to support the application in the container.
Yeah. So with Docker containers, you don't have to run all the OS again, whereas the virtual machines you do. With virtual machines, you would also need more resource utilization, more storage spaces, and more boot up time. However, virtual machines do allow you to run different OS with different machines, as they're completely independent environments. So there are cases for VM, again, and there are use cases for containers, and that is a great chart of differentiating these two environments. So your Docker container has to run on an OS, but your VM has its own OS, right here. So okay, all right. So I will let you guys play around with the package a little bit. Again, focus on this regression model. Okay, so I would go from this directory and go into this, especially the pipeline itself, right? Go through this and also go through the processing steps from the preprocessors, validation, features, errors, data management, and of course the trim pipeline and predict.py. Okay, that's the regression package. And of course we have the config folder. We're all familiar with that because I've talked about that since the first class. And you have the version. Okay, you always want to version your package, whatever package it is. And this is the minor fix. This is major upgrades. This is basically, this is entire software update that does not go back in compatibility, stuff like that. So Python 2 is not compatible with Python 3, right? So Python 3, think about Python 3.8.4 or 3.6.4. 4 is just, something that's minor fixes. Python going from Python 3.6 to Python 3.7, or the other way around, is a major, upgrade of the Python package. But Python 2 to Python 3 is entirely different. Well, I wouldn't say different, but like an upgrade that wouldn't go back, and it's not backward compatible. Okay, that's the version of your package. Okay, so spend some 15-20 minutes. Let's regroup, maybe in 11:10 p.m. EST or 8:10 PST. Then we'll come back and dig more into this repo. Okay, Mesh, would you mind setting up the timer to
Sure. Doing that
11:10? Thank you.
All right, folks.
Cool. Thank you, Mash. So let's get back to our GitHub repo. All right, let me start sharing my screen. All right, so this is the GitHub repo directly from the GitHub. And I open up a bunch of notebooks within this folder, section 04 research and development. Now, the reason why I'm trying to open up these notebooks or trying to show you guys these notebooks is that, you know, if you have been doing data science, you must be asking the question, well, you know, I gotta be using notebooks somehow or somewhere, right? Because you gotta do the EDAs and you gotta test a bunch of things and do, graph a bunch of things and see a bunch of things. If we just start compiling the pipeline, well, where does that, how do you know if you're doing the right thing, right? So, and this is why I've been saying basically we're starting from the phase 3 of the entire life cycle. We skipped all phase 1, which is data strategy, testing, prototyping, interviewing domain experts, and all that stuff. And phase 2 is the data science core development. We skipped all that and we start our course with phase 3. Engineering the machine learning pipeline, but phase 2 paves the foundation for what we do, and these notebooks are exactly what phase 2 is about, and this is where we build the pipeline from or on top of. So to give you a quick idea, this is basically a bunch of or series of 8 notebooks that goes through detailed EDA processes and also feature engineering processes and feature selection processes, and then eventually compile somewhat a pipeline within a notebook, then move everything to a .py file. So that's the entire process. If you go through the class, you will see what's going on. But I just want to show you, this is how the core development or data science core development phase is done, right? And this is where hands-on ML knowledge is. We spent, almost the entire year, Mash and I, Joseph, and a couple other fellows who are also on the call. We went through the entire book going through this. Right, data analysis, some EDAs looking at distribution, missing values, and looking at all kinds of distribution, right? Temporal variables. Temporal variables just means like all the time series or features that deal with time stamps. That's temporal variables. Graphing, bunch of correlation. And again, distribution, histograms, all that stuff. And I'm sure if you've been doing, data science, you have had plenty of fun with that. And this is feature engineering part. So we're basically talking about, hey, how do you handle the missing values, numerical variables, temporal variables, transformation, categorical variables, how do you handle these? Removing rare labels, encoding, and all that stuff, right? So we're familiar with that. Feature selection. So they used a lasso model to quickly run through it and be like, hey, what are the features we can use? And let's just focus on these features and further fine tune our model. That's what feature selection, that's what they did with feature selection, okay? And there are other ways to do feature selection. So that's not the only way, so using a model or using an L1 model like lasso is a way to do feature selection. So because it drives a lot of features down to 0. Okay, and it does have a model training notebook and so on and so forth. And it does use a linear model in the end, linear regression, and it still does pretty well. And I'm sure the RMSE can be better if you fine tune it even more, but that's not the purpose of this this class. And then you have the scoring new data. So basically, I think this is just the same thing, and eventually you score on the new data, I believe. And you have the notebook, feature engineering open source. That's probably something, open source classes, something else. And feature engineering pipeline, feature engineering with in-house software. Okay, so different ways of doing feature engineering. That was just all in research and production modes. And this is where, you know, a lot of the data science projects lie, you know, which, you know, are in research and research and development mode. So eventually they moved every code to this pipeline, right? So the reason why I wanted to show you all these notebooks is that all these codes, right, all these research were important. All these EDA were important, because they eventually, then you can compile that code into do I see them here? No. Okay, so they're probably in this preprocessors. All these previous research can be compiled into these preprocessors. And that's, you know, how you name it. You can name it something else, doesn't matter. And the way how scikit-learn compiles these preprocessors are, you can either do it in a function-based or do it in class-based, okay? And I think class-based is great. But you need to inherit base estimator, transformer mixing, and these imputers or estimators, encoders would match exactly what you have done in these notebooks. Okay, so if you actually go through this course, and you don't have to, but if you go through this notebook at least, you will see all the steps compiled into these preprocessors, okay, defined with classes inherited from scikit-learn base estimator and transformer mixing. And let's go through a couple of them, okay, just as an example. So for this one, categorical imputer, you have an init function, you init your, and you passing your variables, you have a default parameter as none, and you check if it's instance as list. So you want to passing a list, okay, a list of variables instead of just, you know, one variable. So you want to check that type. And the fit just returning itself, fit statement to accommodate the scikit-learn pipeline. So the scikit-learn pipeline needs all your processors or preprocessors to have two functions, okay, at least. One is called fit and one is called transform. The fit function means you're doing everything to be ready for transformation, okay? Sometimes it could be, hey, you know, so in this case, it's just returning yourself. And self, if you're not familiar with OOP, self is just this class itself, okay? And for some of the cases, it does have a fit function. And basically, you're trying to prepare this dictionary with modes. So numerical imputer. So for a lot of numerical features, we're just using mode to impute that, okay, and pass into a dictionary. And that dictionary can then be used in the transform function within the fill NA function. Okay, and you call the in place equals to true, so that every single feature can be filled NA in a for loop. Okay, and as you notice, every time we do transform, we want to copy. Okay, and this is copying a data frame. Okay, pandas data frame, and it's actually a deep copy, not a shallow copy, because it's a df.copy. So df.copy is actually deep copy if you're familiar with pandas. Okay, so and for this transform function, we're just basically fill NA with missing. Okay, so instead of saying, hey, using something else, why don't we just say, hey, for all the categorical features that have NAs, we'll just say, hey, they're all missing. That's one way of imputing it. And I think it's quite a smart way, or quick, simple way of imputing it. Okay, because you can do mean or modes, or you can do median values on categorical features, right? That's one way of doing it. So that's imputing the categorical variables, that's imputing the numerical variables, and we have an estimator for temporal variables. And again, we don't have a fit, necessarily a fitting step, but we do need to have that function in order to feed all these preprocessors into something that's called scikit-learn pipeline. That is the pipeline that we import from scikit-learn.pipeline. Okay, and in this step, we're basically doing some reference variable and minus X feature, and then we get that transformation done in a new feature. Well, not new feature, but just passing into the feature itself, then doing the minus operation. I don't know, I forgot what that reference variable refers to, but that's what it's doing, transform. Okay, and then we have a rare label categorical encoder. Okay, so for some features, there are so many rare labels because they only occur a couple times or one time, and we don't need that. It creates a lot of noise, and it's not helpful for a traditional machine learning model, I guess. So basically we try to calculate the value counts, the frequent categories, and remove the ones that are not as frequent. Okay, so we're preparing this step so that we know how many times each categorical each label occurs within that categorical feature, and then we pass into an encoder dictionary. Then we transform that and encode it. Okay. So that's basically what it is. If it's, I think, if it's rare, we just say it's rare. So basically, we just replace the rare category label with a string rare. That's a very smart way of doing it, and everything else is not rare, and it will just be as it is, right? So any questions on these? I know I'm going through these really quick. Any questions? Everything good? Okay, I take that as no questions. Categorical encoder. Again, it's basically strings to numbers. We have a fit function here, and we have a transform function, and what this is doing is, I guess it's sorting it first, and checking if transformer introduces NaN, and if it, I guess, if it does, then you have to raise an error here. Categorical encoder has introduced NaN when transforming categorical variables. Okay, so that's that. And we have, in the end, a drop unnecessary features. Okay, we have a fit function that just returns itself so that it will just keep running. And we have a transform function that just drops the variables that we pass in that we just don't want. Okay, after we do the feature selection from the EDA process or from the notebooks, we know what features are not important, and we just drop them and solely focus on a dozen features or 24 features that we think are important. Then what you see here is something very interesting. So let me pull this here and split the view. And now what's very interesting is you have everything laid out here, okay, in a pipeline. And again, we're calling the pipeline function from sklearn.pipeline. And you see we're literally feeding this categorical computer to pp.categorical computer, and pp is just basically preprocessors as pp, and preprocessor is just this file, right? We imported this entire file as pp, and pp.categorical computer, which is right here, and pp.numerical computer, which is right here. So we first take care of categorical features, and we take care of numerical features, and we pass in the variables equals to config.categorical variables with NA. So let me pull that config.file over as well. So the way how we got to define what categorical variables with NA and numerical variables with NA first. And the way how we do that is we're literally just defining the config.py. Where are those? Categorical variables with NA and numerical variables with NA right here. Okay, so and how do we know that? Again, from the EDA process, right? We already know that these variables have NAs, and we just define them here so that we don't have to pass in these static variables in our main code to improve readability. Okay, and also these things just shouldn't be changed, and it's better just keep it somewhere in the same place. So okay, config.numerical variables with NA. Temporal variable right here, which is this class, we feed it into here. Again, we pass in the variables that we define. We define the class with 2 init parameters, variables right here, config.temporal variables, and reference variable, drop features. That's what it is. And again, these come from config.py. Okay, and rare label encoders. So now we take care of the rare label encoding, and we feed in this rare label categorical encoder, and we say, hey, the threshold is 0.01 or 10%. Default was 5%. Is 0.01 is the threshold, and maybe it's, I don't know. Maybe it's the value count, I guess, percentage. That's let me see what where TOL gets feed in. Yes, so as long as it's larger or equal to 1% frequency, we're we are saying it's not rare, okay, and they wouldn't be replaced with rare string. And we define what categorical variables are, and we pass them in, okay. And the categorical encoders are basically, you could do dummy or one-time encoding, or you could do something else. I think they're doing something else here, how they encode the variables. I forgot how they encode the variables. You can read this code. They have actually a very smart way of encoding this categorical variable. Dig into the notebooks if you want to learn more. And again, this is developed by professional data science or data science professionals in the industry. So I really like how they engineer the features, even if it's a data set that everyone or most people have dealt with. Very cool stuff. So log transformer, that is in another file. Let me see. Yes, log transformer is in this features.py. So the reason why they separate this is transforming the features. So they want to separate this from the preprocessors. And again, you import these features from regression model.processing from imports features, and features is features.py file, and features.log transformer. And again, we know regression models. With regression models, we need to log transform the variables and the target variable as well, in the features as well. So so that we can have a normal distribution, which would do well with regression models. Okay, so and basically just numpy.log, right? And check that the values are non-negative for log transformation, right? So you want to make sure, hey, are those variables actually negative? If they are negative, you don't want to do that. But if they're not negative, then log transform it. Okay, and you want to check the type as well. Okay, and then eventually you drop the unnecessary features, which is this class. Okay, then you drop the features. Then you do the scalar, min-max scalar. That itself is a direct function that you can call from scikit-learn.preprocessing. And this is a direct function call from scikit-learn library, not something we customized. And then you feed into a linear model called lasso. So we do lasso again in the end with alpha equals to 0.005, and you want to set a random state. Okay, that's the entire pipeline. And then we call that pipeline. Let me move it here just so it's clear. We load the data set, okay, in this train pipeline, and we train test split it. We log the target variable. Then we call the pipeline.price pipe, which is price pipe, which here. Then we fit the X train that comes from here, and we feed the features, entire set of features, config.features, which comes from config.features right here. Then we have the Y train from here, and we have a logger, saving model version. Then we save pipeline. You want to save the entire pipeline, not just your model, entire pipeline, so that you can use your pipeline in the production environment, right? That's the idea. Remember, we read about that in the TFX, the Building Machine Learning Pipelines book as well. You want to make sure you use the same pipeline in the training environment and the testing or production environments, so that you don't have train serve skew. Okay, and pipeline to persist equals to pipeline dot price pipe. That's just what it is here. Save pipeline is a function that we defined in the under the data management folder, data management or data management.py. And save pipeline is basically we're using a library called joblib. Okay, and you can save pipeline with a name, a path, and remove old pipelines and dump your current pipeline and log that at an info level. Okay, and you have a load pipeline, remove old pipeline, load data sets under the data management.py. So everything is pretty modularized. And you have errors.py, which defines some more extra errors that you want to customize. And eventually, you get to your predict.py. Okay, because you've trained it, now you need to predict it. So your input data is a data frame, and you have your pipeline already, you load it in, which you saved, and then you predict. Well, first of all, you need to validate inputs. So that's where data validation comes in. Then you predict your validated data. And you numpy exp your prediction, so that you basically, because everything was locked, right? And now you exponentiate it, so you convert the log values back to the prices, and you have the outputs right here, and you have the results. So that's the entire pipeline, going all the way from data cleaning to prediction. Okay, but it's still not it yet. It's still not the entire pipeline, because we still have to deploy it. We still have to package it in different ways. Okay, but most of the code from data cleaning to prediction is right here. And then you just need to develop your API, which is what we will cover next time when we have the scikit-learn workshop. We will try to go over this REST API with the same package, ML package, and with Flask. Okay, so that's one way of deploying it, or packaging it, so that people can access your model via APIs. Okay, so I've run across time again for 8 minutes. I want to answer questions if you have any questions. I hope that was clear. I know I've run through this fairly quick, but that is a nutshell of what scikit-learn pipeline looks like.
Maybe it's just me having worked with scikit-learn pipelines for a few years now. Seems a lot easier than the TensorFlow extended pipelines.
Yeah, it is certainly easier. Certainly easier, and but it does lack, all the features of engineering, and that come with TFX. That would perhaps, make your system more efficient, more parallelly run. But, scikit-learn, at least the scikit-learn training process, you do you do have the capability, or you do have the option of pass in the n underscore jobs equals to, you know, however many cores you have. So at least you can utilize the number of cores you have with training. It is faster. I've tried it, so, and I've used it. So, any other questions, comments, feedback, please?
This was thorough and extensive. Thank you.
Yeah, no problem. And we will talk more about Docker. Hopefully you can set it up. Okay, you know, it's basically just get Docker and download this. Okay, Docker desktop for Mac. I mean, it is a little easier when you have a Docker desktop. And let me see if I have open up. So this is what a Docker desktop looks like, right? And you have Docker run. Then you can run a container if you want to start a container. But now I don't have any containers running. And this is how you check if you have any images running. Okay, so if you do have images, let's say you do build up an image from your Docker file right here, then it will show up here. And it will say, you know, however megabytes it is. Then you can run that image to, and then an image becomes a container when you type in Docker run. And the difference between an image and a container is just an image is a static snapshot of where your build is, and it's basically down to this, right? That's the definition of the builds. It's a static snapshot of the builds, and the definition of the build is from your Docker file. And the container is a running version of your image that has a program running inside, right? An image doesn't have a program running inside, but a container has a program running inside that will run whatever tasks that you ask it to run. Okay, so make sure you have the Docker set up. We will talk more about Docker in most likely in this workshop. So learn a little bit about Docker. Maybe I'll send out a list of learning material about Docker if you don't know enough about Docker. And we'll talk more about this in workshop 3. And it is a fairly important tool and pretty handy tool as well. It makes your skill so much more powerful when you are able to deploy your own stuff.
Data scientists containerize their end-to-end workflow solutions and share it as a Docker, make it available as a Docker version control Docker image. Done.
Yeah. Yeah. All right. So I think Philip asked, what problems do you run into running secular pipelines in a web service? I think some of the problems could totally be like, you know, if your training data saw something that's, you know, that perhaps is in a certain condition in terms of your data or data formats, certain, you know, data types, and your testing or your production level data or serving data comes in a totally, or comes in a format that your training data has not witnessed before. So, which means your pre-processing steps probably missed a step or two, that cannot take care or is not enough to take care of the new data types or new data formats that only you see within the serving environments. And that will, throw your model off because your model is not prepared for that. And that's where, train, serve, skew, or in this case could even be errors that would come in. And also in a web service, not only you want to validate your data, you also want to, not only you want to validate data on your backend, which is where the model lies, you also want to validate or regulate your data types and inputs on the front end, because, like a lot of times people just type in all kinds of weird stuff, right? And, sometimes even unparsable strings, right? So these things will certainly give you errors and headaches. And you want to try to mitigate that and avoid that, regulate that, validate that in multiple different places so that when it comes down or when it eventually feeds into your model, it's as clean as possible, so that your users can get model outputs in a relatively effective and efficient format. So anything else? Yeah, no problem, Philip. Any other questions? Yeah, thank you. Thank you, Terrence. All right, so I take that as that's it. Thank you, everyone. Thank you, Mash, as well, for co-hosting this session with me. I know it's a lot of stuff, and hopefully you've all got a little bit of time to play around with the code. Again, I would dig into this repo more and understand it, and even take the course if you have time. But if not, just stay with the course, stay with us, and I'm sure you will learn a lot more by the end of this class. So, all right. So next time we'll again switch back to TFX and TensorFlow and the book itself, going through the models now. So things will become a lot more interesting and fascinating, and a lot perhaps more complex and as well. So, all right. Have a good night, guys. Really appreciate it. Bye-bye.